When utilizing static equilibrium, we can analyze machines. First of all, let's talk about what a two-force member is. A two-force member is one that has only two forces acting on it. In a machine, these are usually short links or struts. They can also be bolts, hinges, pins, so on and so forth. And it's very important that you realize when you look at a machine problem what the two force members are. There are a lot of machine problems that are unsolvable without determining this. Other members that have more than two forces are called multi-force members. Let me draw a couple of diagrams to illustrate why this is so important. Suppose you have this particular object in a problem, okay, and that it's pin connected at both sides. Each of those pins is going to produce an X and a Y component. The issue with that is that now we have four unknowns in this one diagram, and that's really too many to solve. So when we use the two-force member, we look at an object and we say, okay, there are two pins and no external reactions. If that is true, then it is a two-force member. And what that means is when we draw it, instead of drawing four forces, we draw only two forces. And those two forces share the same line of action. It reduces the number of unknowns because now we only have two forces and we usually know the angle that that object is acting at. How do we know this is true? Well, just look at this diagram. If we apply a static equilibrium to the x direction, we know that that x force has to equal that x force. If we apply a static equilibrium to the y direction, that y force has to equal that y force. And so if the x and y forces are both equal and opposite, we'll get two forces, the resultant of each of those, that are equal and opposite. So we can simplify that into a two-force member. Whenever you see a two-force member on a machine, you should be replacing it and drawing it like this, with two forces at a single known angle, rather than like this with four forces. Two-force members will have two forces with equal magnitude, opposite senses, and collinear lines of action. Remember that if a member has only two pins and no other external forces, it is a two-force member. Machines are groupings of bodies connected in such a way to transmit, amplify, or change forces in some way. The difference between a machine and a frame is that a frame is typically stationary and machines usually allow relative motion between their members, even though we're going to always view them in their frozen geometry. So for example, this set of pliers here has two parts. There's this handle and jaw, which are all one piece, and there's also this handle and jaw, which are all one piece. And they're connected by a pin here in the center so that they can move. Also over here, if we view this tractor, there are a number of machines here, but we can just analyze the bucket. We've got the bucket itself. We've got this short link here. We've got this member. We've got this piece, this cylinder, this sort of V-shaped piece, this cylinder, this C-shaped bracket. All these members together compose a machine, and they allow relative motion between each of the pieces. When we look at machines, we use the method of members. So first of all, we isolate each member from its surroundings, and we draw the outline shape of each member. So we're going to have multiple free body diagrams for each of these problems, as many free body diagrams typically as there are parts of the machine. We will apply all the forces to each of those members, both known and unknown. We will then label each force, make a sign convention, identify all of the two force members, and then solve for the required values. Now this is a highly simplified explanation. Typically what happens is you solve a force on one object, then after you solve for that force you move to another object and apply it there, and then solve for the other forces. The method of members is going to be by nature a dependent solution in much the same way that the method of joints was. We're going to be using forces we solve on one particular part of the machine to solve for forces on another particular part of the machine. Here we have a clamp and a wooden block inside of its jaws, And the problem asks to find the force that the clamp exerts on the block. A couple of notes before we start. Probably the first thing to do is look at the diagram and figure out how many different pieces and how we're going to treat this. In the end, I'm going to break this into 5 separate parts. I'm going to have the block. I'm going to have this bottom jaw here. I'm going to have this top jaw, this top handle, and the bottom handle. Now, it's true that we could break apart this part of the top jaw. This is a threaded rod that goes through it, but it's not going to actually add anything to the analysis at the end of the problem, since there's just going to be a single vertical force going in this top jaw. So there's no need to do that. We can draw those as one. I highly recommend that you fully understand what the machine is and you ask any questions about the problem before you start to analyze it, because if you start with a faulty assumption, you're not going to be able to solve it correctly. After breaking up the original diagram into individual free body diagrams, the next thing to do is to apply the forces on them correctly. Let's start with the block. Because the clamp can only provide vertical forces on the block ends up being a two-force member. There's one force going down and one force going up. They are collinear, have equal magnitudes, and opposite senses. Now let's go to the top jaw. The first force we want to apply to the top jaw is the force of the block acting back on the jaw. And notice the sense of this force. It's going up, such that if I were to put the block and the top jaw back together, F would cancel out with F. Now, I don't actually know which way F is going right now. I know its line of action, I just don't know whether it's going up or down in the block. But the sense of F on the top jaw has to agree with the block such that when I put the two pieces back together, that force cancels out. Points D and A are 2 pins, and as you've learned, a pin produces 2 forces, an X and a Y. I have not yet done anything with D and A on any of the other diagrams here. I can assume dx and dy in whatever direction I choose. So there's dx, dy, ax, and ay. Now I'm going to go to the bottom jaw. On the bottom jaw, we once again know force F. Since force F is going up on the block, it has to be going down on the bottom jaw. Coming over to point D, I've already assumed dx and dy on the top jaw. When I draw the forces over here, they are still assumed. However, their directions have to agree with whatever I've already drawn so that when I put the two pieces back together, the forces cancel out. Therefore, my dy on the bottom jaw must go up, and my dx on the bottom jaw must go to the left. That's only because I drew dy going down and dx going to the right on the top jaw. If I would have assumed those in the opposite direction, if I would have assumed dy up, then I would have had to draw dy down on the bottom jaw. Looking at point C, I have not yet assumed any directions for any of the C forces, so I can draw those in whichever direction I wish. If you're curious to know why I'm drawing them the way I am, it's not because I have an inkling as to which way they're actually going. It's because I'm drawing them in the easiest way. So if you look up at the top jaw, I drew dy going off of the object rather than onto it because I figured that would just be easier to look at. Now let's come over to the top handle. I have points A and B, once again 2 pins. And since there's more than just those 2 pins, I will have an X and a Y. If this P force was not here, this would be a 2-force member, and the 2 forces would be collinear right at A and B. However, since P is present, we've got an X and a Y force each at A and B. And I have not yet used point B, so I can assume whatever direction I like. I have, however, used point A. Up here, I've drawn AY going down, so here I have to draw AY going up. Here I have AY to the right. Here I have to draw it going towards the left. Coming over to the bottom handle, I've already assumed forces for C and D. CX has to go towards the left because CX over here is going towards the right, and CY has to go down here because CY is going up here. These are all still assumptions, they just have to agree with each other for this to work out. Likewise, point B, I've already assumed those. BY is going down here, so it has to go up here, and BY is going towards the left here, so it has to go towards the right here. Now we have to look at how to solve this problem. We're really looking for F. We're trying to find what the force on the block is. And in order to do that, we're going to have to trace the force through each of these pieces to get back to the force F. So let me walk you through my solution procedure. I first looked at the top handle and the bottom handle. That's the only place I have a known force, so I'm going to have to start with one of those. It doesn't actually matter which one you start with because they're both solvable, but it looks like the top handle is going to be easier to me. So looking at the top handle, we would first look at AX and BX. I would want to solve for those two forces. How could I do that? Well, I could sum moments at point A. If I sum moments at A, that'll cancel out AX, AY, and BY because BY goes through point A. So I can use P to find BX. Likewise, if I sum moments at B, I can cancel out AY and BY and find AX. That doesn't actually solve the problem yet because you'll notice I still don't know AY and BY and I can't find them. I can sum forces in the Y direction, but I would still have two unknowns. So after that, the next step then is to figure out what AY and BY are. And probably the best way to do that is to come over to the bottom handle. If I come over to the bottom handle, I've already solved for BX. If I want to find BY, the solution is to sum moments at point C. Summing moments at point C would cancel out CX and CY, leaving BY as the only unknown. I can use BX and P to find BY. Now you'll notice as I'm doing this, I am finding dependent solutions. You're basically chasing the unknowns around the problem from one diagram to the next, back to the first one, and so on and so forth till you get enough knowns to be able to move to the answer. So be careful there, since it's not an independent solution, there's no good way to check your answer. After we found BY, we can come back to the top handle. I will have solved for BX by summing moments at point A, AX by summing moments at point B, BY by summing moments at C on the bottom handle. Now I can solve for AY. After solving for AY, we can come up to this. We know AX, we know AY. And the answer would be found just by summing moments at point D. Summing moments at point D would cancel out dy and dx. You can use AY and AX to solve for F. Now that's very few steps to actually be able to solve this problem. However, there's a lot going on in this diagram. There's a whole lot of unknowns, and it can be very confusing. I encourage you to try to do what I just did, to look at each diagram and say, okay, if I sum moments at this point, what happens? How many unknowns do I have? And if you get to a point where you only have one unknown, solve it. Then see if you can use that value to solve for another value and chase it around the problem until you find what you're looking for. Take advantage of things such as two-force members. This block is a two-force member. Its two forces are collinear, so we know the angle. There are other two-force members. Remember, a two-force member is anything where there's only two forces, and one of the ways to find that is if there's a member that's pin connected and has no external reactions. It is a two-force member, and you know its angle. The second thing to note is that you probably want to start where the known value is. The third thing to note is take advantage of forces that are collinear, such as this. Even though this isn't a two-force member, AY and BY are in line such that when I sum moments at A, it's going to cancel out BY. You can actually solve the bottom handle first. However, if you sum moments here at this location, you're going to get CX and CY. If you sum moments here at C, you're going to get BX and BY. If you sum forces in the Y direction, you'll have BY and CY as your unknowns, and if you sum force in the X direction, you'll have BX and CX as your unknowns. That's 4 unknowns, 4 equations. It is solvable, it's just not nearly as nice as this method, starting with the top handle. So look and see if there's any collinear forces that can help you out. So after we write our assumption of static equilibrium and our zero statement, we look at what forces produce no moment around point B. I want to note before I go on that I've written what free body diagram I'm working with. That's important because there are 5 free body diagrams here. So make sure you say which one we're applying static equilibrium to. So around point B, BX goes through point B, BY goes through point B, and AY goes through point B as well. So those 3 forces will not produce any moment. My equation then becomes AX is going to produce a positive moment around point B, and its perpendicular distance is A. P is going to produce a negative moment around point B, and its perpendicular distance is E. So AX equals P times E over A. Now we can plug the numbers in. Once you solve that, we'll find that AX is 210 newtons. The positive sign here, it means we assumed correctly, so AX is indeed going towards the left on the top handle, which means AX is going towards the right on the top jaw. It's really important that you look at that sign. I do not recommend using vector signs here. Technically, it's not incorrect if you draw a vector sign and you also say what free body diagram. However, it's best practice just to use the actual positive negative sign, because that's harder to confuse. If I just draw an arrow to the right, does that mean it's going to the right on the top jaw or the right on the top handle? It's much more confusing to figure it out. Also, this is not in tension or compression. It's not a two-force member. Only two-force members are in tension or compression. We just solved for AX by applying static equilibrium to moments with respect to B on the top handle. Now I'm going to apply static equilibrium to moments with respect to A on the top handle, and we're going to solve for BX. When we look at point A, AX, AY, and BY all go through point A, so they're not going to produce a moment. 0 then equals, BX is going to produce a negative moment around point A. Its distance is A. P is also going to produce a negative moment around point A. Its distance is E. Solving for BX gives this. Now we can plug the numbers in. And we will find that BX equals a negative 210 newtons. Now you might look at this and say, well, there's only two forces. Why didn't you just solve for BX using static equilibrium in the x direction? The answer for that is because I would rather solve for BX independently. I solve for BX here without the use of AX, so I have a lot more confidence in my answer. It's obviously correct because AX was positive 200 going towards the left on the top handle. BX is a negative 200, which means it's going towards the right on the top handle. And if I add those two values together, I get 0. So I'm using static equilibrium in the x direction to mentally check my answer, but I'm solving independently as much as possible. I will not be able to solve the whole problem independently, but wherever I can, I like to use independent solutions because that gives that much more credibility to my answer. Once I know BX on the top handle, I can then move to the bottom handle. If I sum moments at C on the bottom handle, it'll cancel out CX and CY. I know BX, I know P, and I can find BY. When we sum moments at point C, CX and CY both cancel out. So BX here is producing this type of rotation, which we will call negative. And its perpendicular distance to point C is B. P is producing positive rotation, and its perpendicular distance is E plus F. BY is also producing positive rotation, and its perpendicular distance is F. Solving this equation for BY gives this, and now we can plug the numbers in. Notice that I included this sign when I plugged in BX. Since I got a negative for BX in the top handle, that means that BX is also negative on the bottom handle, which means it's going towards the left on the bottom handle. That's where my negative sign comes from. So BY equals a negative 1125. Once again, the negative sign tells me it's incorrect on the bottom handle, and it's also incorrect on the top handle. Once we know BY, we can bring that information back up to the top handle to find AY, and I'm going to use static equilibrium in the Y direction. Now you might ask, why did I use static equilibrium in the Y direction here, but I didn't use static equilibrium in the X direction to find AX or BX? The answer is because there is no way to solve for AY independently. Anything that I do on here to cancel out AY is also going to cancel out BY. I can pick A, I can pick B, I can pick a point up here, down there. It's going to cancel them both out because they both share the same line of action. The only way to proceed here is to use static equilibrium in the Y direction. This is going to produce a dependent solution, however, it's the only method I can use. 0 then equals, AY is a positive AY, BY is drawn as a negative BY, and PY is a negative P. Solving for AY yields this. Now we can plug the numbers in.
Note once again the sign comes with by. Since we got a negative for by, that means its direction is incorrect, which means by is actually going up in this diagram. And we find that ay is a negative 1050. After we found ax and ay, now we can actually solve the problem. Coming over to the top jaw, we'll see there's 5 forces, but we can cancel out 2 of the forces if we sum moments at point D. We don't know dx and dy. Summing moments at D will cancel them both out, and we can find f using just ax and ay. So when we sum moments around D, both dx and dy have no perpendicular distance, therefore they're not going to produce a moment. F is going to produce negative rotation around D. Its perpendicular distance is c. AX is going to produce negative rotation around point D, and its perpendicular distance is a. AY is also going to produce negative rotation around D, and its perpendicular distance is d. Solving this for f gives us, and now we can plug our numbers in. Note the negative sign that was included when I plugged in the value for AY. And we'll find that F equals a positive 562.5 newtons. When you do a machine problem, as I said, it's like you're chasing the unknowns around the problem. You might have to mentally work through the problem more than once, and I highly encourage that. Don't start writing things down necessarily, but think about how you're going to step through the problem to find the unknowns to get to where you're going.